Hey folks, Darren from Fervent Astronomy. I'm here to give you an overview of the Fornax Mounts 52. This is Fornax's smallest German equatorial mount, and as the name suggests, it has a payload capacity of 50 kilograms or 110 pounds. So we're going to take a look on the inside and on the outside, and we're going to give you a good idea about what makes this mount special. So at first glance, it's obvious that the Fornax 52 is a German equatorial mount. It has the traditional declination and right ascension axes that you're most likely familiar with if you've seen a mount of this type. And one thing that is really clear upon seeing this mount in person is that it is really, really robust. Solid metal, it is 77 pounds or 35 kilos on its own without counterweights. And when you're dealing with a mount that big, it is a observatory mount, or in the case of the 52, also a mobile mount, with one caveat that you have to have an extremely sturdy tri-pier. Now with a 110 pound payload capacity, this mount can obviously take a huge range of equipment. And if you're going to be doing astrophotography or some other type of imaging, the recommended payload is slightly less, as is normal with many mounts, at 30 kilos. So that's roughly 66 pounds. That's the manufacturer's suggested number. Your mileage may vary here, and no doubt a lot of you might be able to put even more equipment on this with some good auto guiding or perhaps some encoders. But as a general guideline, you'd want to keep your payload in that 65 to 70 pound window, which is a lot of telescope. So what makes this mount special isn't any gimmicks or other quirks that have been added on top of it. Its job is simply to turn very slowly in the proper direction and keep a lot of weight on top, turning at precisely that speed. For anyone who's used a German equatorial mount before, the design is going to be very familiar, but as a little bit of a refresher, we have our right ascension axis here. Here we have the motor box and the gearbox. And this part is stationary. As it tracks the sky, it does not move. Up here, we have the gearbox and motor box for your declination axis. Now, when the declination axis turns, this plate will move. When the right ascension axis turns, the entire declination, gearbox, motor box, scope, and counterweight will all rotate back and forth. This mount does require a meridian flip. While we are going over the Fornax 52, it's important to note that with a couple of minor design changes, everything that we go over here is applicable to the Fornax 100 and the Fornax 150, or depending on when you're watching this video, the Fornax 102 or 152, and so on and so forth. As you might expect, those mounts would have 100 kilo and 150 kilo payload capacities at the maximum. And again, the general design of these mounts is very consistent. The Fornax 52 is a belt-driven mount. We have a large gear located here, which is driven by the worm gear located approximately here. And then the motor here in the drive box uses a belt to drive the worm gear. And in this way, we get some really nice, smooth tracking, with the worm gear having a period of about 7.5 minutes. The error on this mount over that 7.5 minute gear period is only plus or minus 6 arc seconds. What that means is that even unguided, if you're using a wider focal length optic, you can get some really well tracked shots. Even using a longer focal length, you might even be able to push it for a couple of minutes before you notice any star trailing. That said, with a mount of this size, quality, and likely the type of optic that you're going to be putting on it, it is recommended that you do either some type of guiding for astrophotography or use a encoder-based system, either a telescope drive master or one of the dual encoder options. To go over the outside and tell you what you're looking at here, we of course have our two drive boxes. There is a slow-mo control in red on either side. This connects directly to the worm gear, and by turning this lever you can adjust that axis over that 7.5 minute gear period. Up on the top face of the gearbox here on the deck axis, or the bottom flat face here on the right ascension axis, you'll notice acrylic windows. These acrylic windows give you a look at the interface of the belt with the worm gear, and it will show you as you turn it how the gear is moving. Here we have the worm gear from this mount to give you a closer look at what's actually driving the main gear. This is the stepper motor used in both drive boxes of the mount. It's a 200 phase step per revolution motor at 1.3 nanometers. On the top of each drive box, you'll notice a black compression adjustment. This adjustment controls the compression of the spring, that is in turn compressing the worm gear. This helps to take up any backlash in the gear interface, and is one of the reasons why there is minimal to no backlash with Fornax's Equatorial mounts. On the sides of the drive boxes, you'll notice that there are DIN connectors. This is for connecting the interface with the motor drive controller. Currently, these mounts are configurable with the Ursa Minor MC5 controller. You can also get the mount stock with no controller and add your own, or in the future, there might be different controllers available as well, again, depending on when you're watching this video. There are a number of different mounting options for your optics with these mounts. Here we have a dual Vixen style, Losmandy style saddle plate for, again, Vixen or Losmandy style dovetail bars. This is the regular size. There's also an extended size that gives you a bit more room, and the mount is also configurable with a plate that if you have an OTA that uses rings, you can attach the rings directly to the plate and get a really secure mount. This is of course especially useful if you're doing an observatory setup and if you are not switching back and forth between different optics. At the base of the right ascension axis is a bushing that allows you to connect a universal polar scope adapter, which gives you the option of using Fornax's polar scope or indeed any polar scope available on the market, including some of the electronic ones, and is common with this type of mount. There is a hollow through the right ascension shaft and a light path that comes out the top of the mount. There is a dust cap located on the top right here that allows you to keep this optic in there and keep it clean. And of course, another design element of this system is that the declination axis has to be in the proper orientation, as there is a split in the shaft that allows the light to pass through. So in order to successfully polar align your mount, you do have to make sure that the deck axis is pointed the right way. I'm likely not the only one who sat there looking through a blank polar scope wondering what the heck is going on, only to realize that I had my telescope pointed 90 degrees in the wrong direction. As this mount is developed around a robotic workflow, you'll notice that the clutches on both axes lack a quick release. Instead, you need to use an Allen key, and that will allow you to loosen the clutches, remove them if necessary, or generally just make any adjustments that you need to make. Both clutches rotate 360 degrees, which will allow you to reposition, especially the declination clutch, to ensure that you have good access to that Allen head screw so that you can make any adjustments in the future that you need to. Any greasing of the gears or other service will require the removal of the attachment plate for your optics and the clutch on the declination axis, or the entire polar alignment system and clutch on the right ascension axis. That then gives you access to this plate, which you can remove and inspect the gears inside. We'll go into that in a later part of this video and give you a look at the guts of the mount. Polar alignment of the mount is done in the traditional way with Alt-Az controls. Here you have your altitude control. It is a stainless steel and brass system that allows you to raise or lower the altitude of the mount. When you've got your altitude locked in, there is a lock nut on either side here, Allen head bolts, and you can just lock it down nice and tight. The azimuth, of course, is controlled with the traditional push-pull controls, and once you have that adjusted, on either side of the mount there is another bolt which allows the mount to lock in place. The mount is actually held down by these same bolts on either side, so it is very important that you securely tighten them. Once secure, the mount is rock solid and isn't going anywhere. At the bottom of the declination axis is the interface for the counterweight shaft. It is threaded and the counterweight shaft just screws right into the bottom there. Here we have our counterweight shaft. It's a hollow tube threaded on this end, again to go into the bottom of the declination axis. And of course it's got a lock nut on the other end here. Toe saver, it's always important to have. The weights are configurable to whatever you need, and Fornax can ship any type of weight that you might require. So if you're building a custom system and you need a custom weight size, just contact us and let us know. Fornax's equatorial mounts can be configured in a number of different ways, and options are available for a dual axis encoder system where you can get absolute encoders for both axes. This is an ideal setup if you're going to be doing any type of remote setup or robotic telescope, and that is an option that is available both on this mount and on its larger siblings. As far as bringing down the periodic error from that plus or minus 6 arc seconds per period down to a 0.5 arc second per period error, you have a couple of different options. You can, of course, use the absolute encoders or a telescope drive master, which is essentially just a right ascension axis encoder. Or you can do what many people do and do auto-guiding. This mount is compatible with standard auto-guiding protocols. All you have to do is make sure that the auto-guider that you're using is going to be compatible with the drive box that you choose. If it's going to be the Ursa Minor boxes that are sold with the Fornax 52, 100, and 150, then you'll have no problem. If you're using a different system, just make sure that you double check before you commit any dollars to anything. Next, let's take a look at the controller interface. In this case, we're going to be showing you an Ursa Minor MC3 controller, which was the previous generation basic controller for this mount. It comes with a motor drive box and a hand controller. It is now upgraded to the Ursa Minor MC5, which has improved connectivity options. Here I have the Ursa Minor MC3. You can see it's a pretty utilitarian electronic box with all the typical interfaces. Here we have the guider interface we have for the hand controller. This version did not have onboard wireless, so you have a Bluetooth controller, you have USB power, and a DSLR trigger on that end. Here on the back you have the power input, which is anywhere from 12 to 30 volt DC, maxing out at 2.5 amps. And you have your on and off switch, your deck motor drive cord, and your RA motor drive cord ports. Here we have the cable connector that connects to the mount on this end with the DIN, and then with a D sub on the other end to the drive box. The port here is keyed, and so we'll just put it into the deck axis there. Put the locking bolt on, then we can take our D-sub cord and attach that to the drive box. It's recommended that you mount the actual drive box to the side of your pier or what have you in whatever configuration works best. These cords are actually quite long, so you don't have to worry about losing slack. And here the cable management is manageable. The Ursa Minor MC3 and MC5 systems both come with a hand controller, which gives you all of the control you need. You can interface with a computer and use software there. However, if you're going to be out in the field and wanting to keep things simple, the hand controller does a really good job. You can adjust everything, voltages, gear ratios, what have you, from here. And it connects on the bottom there, both with a USB to the computer to update firmware, or with a Cat5 or Cat6 cable just into the bottom. Here we have the end of our power supply, and the male connector just fits into the female receptacle on the drive box, and it has a lock which allows it to remain secure so you don't accidentally trip over anything and shut your whole system down, which again, from personal experience, I've done more than one time with mounts over the years. And it's got a little release lever which just allows you to remove it. So now that we've gotten to know the mount a little better and have taken a look at how to connect it to its electronic interface, let's take a little dive inside and see what's actually happening behind the metal exterior here. Now we're going to take a little look inside, and to start we'll have to remove the saddle plate here. There are 4 hex head flush bolts in a cross pattern, and just remove them like so. Got our saddle plate. This is the mounting plate that sits in between the deck shaft and our saddle plate, and it's what provides the leverage for the clutch. You can see now that I've removed it, the clutch has come completely free. The tapered end, or the beveled end rather, on the inside is what pushes down into the shaft, providing that rock stable interface. You'll notice the clutch is a split ring, and it has a Allen bolt right there that allows you to adjust the pressure. Now that we have that removed, we're going to move into taking these Phillips screws out. Here we simply remove our cover plate. You can see that there's a gasket on the plate there that fits around the shaft and the main gear there. And this is what is providing a lot of the protection. The plate here goes over top of the cast drive box and basically keeps everything out. If you really want, you could apply some silicone or a gasket material around the edges if you were essentially extremely concerned with maximum weather resistance, but otherwise there's gaskets at all the openings there which help provide that sealing. Here we're going to remove the main gear. We're going to start by backing off the spring on the worm. If you can see, it's actually a rather long piece, and it's made of plastic, threaded, and there's a receptacle inside here. That receptacle takes the spring, and this spring is what provides the force to the worm here. Now we're just going to gently press on the opposite end of the worm, press it back toward where that spring was sitting. The worm itself is mounted. You'll see that there's two Allen head bolts down here. These are what hold this end of the worm gearbox in, and we're just going to push on the other end to provide a little bit of space, and then we're going to remove our main gear. So here we have our main gear. The gear itself is well greased, so be prepared that if you're going to be doing maintenance in here, you are going to get a little bit dirty. The drive gear itself, you'll notice, has two components. One, most of the body is actually stainless steel, and then there's a ring of brass around the outside that is held together with 6 hex head screws. This is, of course, the drive surface for the worm gear. The strength of a really large drive gear, of course, is in the error of the mount. It really helps smooth out any tracking errors and overall make for a better experience. Inside the mount here, there is still the worm box, and behind it, the stepper motor here as well. And this whole drive system here is held onto the mount via 4 bolts with the shaft through the center. On this surface of the gear, you can see is where you have the beveled surface that provides an interface with the clutch, allowing you to essentially force this gear down and form a solid connection with the actual shaft. Again, here we have our worm gear, and just to illustrate, of course, as the worm turns, it causes the main gear to turn as well. And that is the primary means of driving both axes. We'll take a little bit of a closer look here and give you a really nice look at some of the other components inside. There's a small Allen set screw that holds the handle onto the end of the worm. Now here we've freed up both the worm box and the track that the worm box rests in, and we've also freed up the manual handle. That allows us to remove the gearbox from the mount. Here we have the track that the mount's worm box sits in. Here we've now freed the worm and stepper motor from the casing of the drive box, and we'll take it out here and show you. Just to give you a good up close look. Stepper motor, worm drive box, worm gear, belt drive system. Got a large drive gear on the worm itself. And of course, we have the worm and this cutout which accommodates the removal and replacement of the main drive gear. On this side, these splits allow some movement and flexure through this box, which when the worm box is pressed with that spring allows the worm to be pressed very firmly into the drive gear, removing any backlash. The DIN connector is connected in through here, and it has interface cable which connects directly to the motor. And of course, once all that's out of there, we're just left with the hollow shell of the cast drive box. The drive box is held into the mount here with 4 bolts held into this piece right here, and the same general layout is true of the mount on the right ascension axis as well. This has been your look at the Fornax 52 and by extension the Fornax 100 and Fornax 150 series mounts. I hope you've enjoyed your tour of the outside and insides of this mount, and I hope you found it informative. If you have any questions at all, please head over to ferventastronomy.com and drop us a line. And until next time, clear skies.